It's math class once again. Are you ready to learn more about calculus? You might want to print out Learning Worksheet 5.2 and to prepare your materials. A notebook or paper for solving and taking down important points will be helpful in understanding the lesson. Settle down and we will proceed with the topic. Integration by substitution. We are now in the third part of calculus. You have learned from the previous lesson that antidifferentiation is the reverse of finding the derivative. Therefore, if g of x is equal to f prime of x, then f is the antiderivative of g, written using this notation. Let us recall further antidifferentiation by solving the following examples. Find the antiderivative of 5x squared plus 7 over x cubed. As we consider the reverse of differentiation, we think of what function has 5x squared as its derivative. We know from the power rule that the exponent 2 was obtained by subtracting 1 from the original exponent. Hence, the antiderivative will have x squared plus 1. We also know that the coefficient 5 was a product of the original exponent and a number, and therefore we divide 5 by the new exponent, which is 3. Similarly, since 7 over x cubed can be expressed as 7 times x to the negative 3, we can consider the antiderivative to have an exponent of negative 3 plus 1. Then, we divide 7 by the new exponent, which is negative 2. So for the antiderivative, we have 5/3 x cubed minus 7/2 x to the negative 2 plus the constant c, or 5/3 x cubed minus 7 over 2x squared plus a constant c. If we are given a trigonometric function, we do the same thing, which is the reverse of differentiation. Given tangent squared t plus 1, we know that this is equal to secant squared of t. And we learned from our lesson on derivatives that secant squared of t is the derivative of tangent t. This time, let us find the antiderivative of quantity x to the 5th plus 2 raised to 9 times 5x raised to 4. We can choose to expand this expression so that we will be working with a polynomial. However, having an exponent of 9 will result to a long process. If you look at the terms involved in this function, you will recognize that 5x to the 4th is the derivative of x to the 5th plus 2. With this observation, if we let x to the 5th plus 2 be equal to s, then applying implicit differentiation, the derivative of s with respect to x is equal to 5x to the 4th. Therefore, ds is equal to 5x to the 4th dx. Substituting s, we will now find the antiderivative of s to the 9. This results to 1 over 10 times s raised to 10. plus the constant c. Replacing s with x to the fifth plus 2, the final answer is the quantity x to the fifth plus 2 raised to 10 all over 10 plus c. In integration by substitution, what familiar concepts did we apply? We considered the chain rule. We applied implicit differentiation and anti-differentiation. Let us move on to another example. Find the antiderivative of c squared over the square root of quantity 1 plus z cubed. Recognizing that z squared is the derivative of 1 plus z cubed, we can let s be equal to 1 plus z cubed. The derivative of s with respect to z is equal to 3z squared. So ds is equal to 3z squared dz. But looking at our original expression, we want to replace z squared dz. Substituting s and ds over 3, we now find the antiderivative of 1 over the square root of s times ds over 3, or 1/3 s raised to negative 1/2. S will have an exponent of negative 1/2 plus 1, while the coefficient is 1/3 divided by the new exponent, which is negative 1/2 plus 1. Simplifying, it is equal to 2/3 s raised to 1/2 plus the constant c. Substituting the original expression for s, the final answer is s square root of quantity 1 plus z cubed all over 3 plus c. In the next example, we are looking for the antiderivative of quantity 2x cubed plus 5 raised to 3 times 12x to the fifth. If we let s be equal to 2x cubed plus 5, the derivative of s with respect to x is equal to 6x squared. Thus, ds is equal to 6x squared dx. Making the necessary substitution, we replace 2x cubed plus 5 with s and 6x squared dx by ds. Thus, we have the remaining 2x cubed in our expression. But since s is equal to 2x cubed plus 5, we can express 2x cubed as s minus 5. And we work with the expression x cubed times the quantity s minus 5 ds. We then expand the expression, find the antiderivative of s to the fourth minus 5s cubed. This results to s to the fifth over 5 minus 5s to the fourth over 4 plus the constant c. Replacing s with the original expression, the final answer is quantity 2x cubed plus 5 raised to 5 all over 5 minus 5 times the quantity 2x cubed plus 5 raised to 4 all over 4 plus c. Lastly, let's have an example involving a trigonometric function. Find the antiderivative of cosine 4n. Letting s be equal to 4n, the derivative of s with respect to n is equal to 4, and therefore ds over 4 is equal to dn. Replacing 4n and dn, we find the antiderivative of cosine s ds over 4 which is equal to sine s over 4 plus the constant c. Thus, the final answer is the sine of 4n over 4 plus c. Wrapping up, antidifferentiation is the reverse of finding the derivative. Hence, we apply opposite operations in finding the antiderivative. In the examples that we discussed, they involved the chain rule, and this required the integration by substitution to find the antiderivative.